introduce our seminar speaker today, Dr. Michael Todd. He's from UC San Diego, where he's the chair of the structural engineering department. He got his degrees from a small school not far from here. It's this tiny blip in North Carolina. It's got some blue color in it.
Hey, we share a common hatred of the Tar Heels, right? Okay, that's what I thought. Duke is not the terrible enemy here, but okay.
So anyway, he got all his 3 degrees at Duke, and then he's been there at San Diego for about 22 years.
Almost 22 years, yeah.
And very well known in the area of structural engineering, of course, specifically in structural health monitoring. Working in a variety of ways of solutions for structural health monitoring. And it's very accomplished. I know you have seen the CV, but I'll read a few things. He won the 1999 Alan Berman NRL Publication Award, 2003 and 2004 NRL Patent Award, the one Leibig Center for Entrepreneurship and Technology Advancement Fellowship winner. But now recently, he's recently won the Lifetime Achievement Award from the SHM Society, and he's also the SPIE Non-Destructive Evaluation Lifetime Achievement Award, and recently, 2024, he got the Roy Sharp Prize for Outstanding Contribution to NDT. So it's my pleasure to have Dr. Michael Todd here at North Carolina back. So
I love being back in Raleigh. That's great. And thanks so much to the department. I think I was here 10 years ago? I think exactly 10 years ago. So it's been a while since I've been back to Raleigh. But anyway, so I was kindly introduced as being an expert at structural health monitoring. I'm actually going to talk very little about structural health monitoring today, although it's underpinning one of the fundamental underpinning technologies for doing long-term monitoring, obviously, for asset management of structures. So at the end of the day, it's all about risk. Managing a structure, from our perspective, is all about risk. And we're going to talk a little bit about how to model that and combine a lot of different things into a capability to do life cycle modeling and make risk-informed decisions about what to do with your structure, okay, whether it's maintenance, retirement, and that kind of thing. So the motivating area is actually a little more civil focused. Even though I'm a mechanical engineer by training, we have support, a large-scale support of a team of us that I lead from the U.S. Army Corps of Engineers. Okay, most people think of that as a civil-focused organization. But they operate and maintain all of the United States Inland Waterways Navigation Corridor. You can see all the rivers and some of their sites that they are responsible for. This is a $500 billion capital investment that the United States has made in inland waterways commerce. There's about 236 lock chambers. Anybody know what a lock is? Yeah, most of you, some of you. You're going to see some pictures. 236 lock chambers along these rivers that have been operational, and here's the key, more than 50 years. You can imagine they're not in the best shape. Okay? And it turns out unplanned lock closures at any one site, $3 to $4 million in loss per day. So that's a lot of commerce not getting through. If you block the river from a lock and dam closure, it's going to be very hard to move commerce, right? So you can see where the motivation is coming from. So one of the components of these inland waterway systems is a miter gate. That's a lock chamber, by the way. They're basically boat elevators. Right? So where there's big different elevations in river heights as the boats navigate, they go into the lock chamber, they pump the water up to raise the boat, seal off the back and send the boat out the other side. One of the fundamental components are these miter gates, these giant, they can be 150 feet tall, okay? Steel structures that open up. The whole thing rests on this thing called the ball and pintle. It's only this big. There's a lot of stress down there. It's underwater. The lower quarter to a third of most miter gates is always underwater. Generally, these gates are loaded by differential hydrostatic pressure, right, from the water, up and down. The water level is going up and down. Lots of stress, although not highly dynamic stress. There's definitely some dynamic stress, but it's not really a a massive dynamics problem. And our main failure modes, we have a lot of problems along the main load path of the gate. That's where the gate is sitting on this ball right here. That's my hand pointing at the load path area. You start to have loss of contact between the gate and the wall, the supporting wall. That's bad. Cracking, corrosion, lots of things going wrong in these gates. So there's no point to do life cycle modeling or management. You can't do it without modeling. Why? Because you don't know the future. I don't know where my asset is going to be operationally in 20 years. So modeling fundamentally underpins doing asset life management. And so sitting underneath some of the things I'm talking about today is going to be a lot of fundamental structural models. So, for example, you might see here a miter gate. That's the Green Up Lock and Dam in Ohio. There's a crack that was taken by an underwater drone. We have to be able to integrate physics-based modeling capability, a runtime fast version of the model, because there's thousands to hundreds of thousands of degrees of freedom in such a complex model, plus all the uncertain variables. It takes months to run, one run. So we can't do that. We have to create surrogates. And then we have to forecast the future. Where is the state of operation going to be in N years, right? So that's a pretty complicated process. And the way we're bringing data in to inform those models, there's a lot of ways, but there's two primary ones. Strain gauges, good old strain gauges. Yes, they can go underwater. I was surprised. And drones, underwater drones. Also aerial drones for the part of the gate that's always exposed. So we're getting images and then performing different kinds of feature extraction techniques on images to be able to quantify states of damage. All right? And then once we do that, we create the so-called hurricane charts. That's what I call them. And that's, here's where we are now. Here's our limit state. When are we going to get there? All right? So that's really, that's sort of the underlying workflow. Okay? And then from this, if we can simulate this whole process, it's not easy, but that's what we try to do. The idea is to continuously over time shrink our uncertainty on prediction of when we reach critical decision states. Right? I mean, that's the concept, and it's really pretty straightforward. This was all motivated by the Marine Transport National Strategy. They actually said reliable movement of people and commerce, and the word reliable is the key word here. And then the ASCE came along and said, we're going to do this by relying in real-time access to databases, sensors, diagnostics. And I said, hooray, because this is my area. I want to get involved with this. And this is how we were able to get an Army Corps Center of Excellence into looking at this. So we basically want to take the motivation and the investment of the U.S. in its waterway system to try to do cradle-to-grave life cycle management. So that's the underlying motivation. How to convert all the data we could get, plus our modeling capability, into actionable information. And it's, needless to say, complicated. It's not just civil engineering. I'm not even a civil engineer. It's everybody. Everybody except maybe the bio guys, sorry. On deck, all right? Has to be on deck to solve these problems. Statistics, as you're going to hear about today. Behavioral economics. In an engineering program, yes. Because people make asset decisions and people make uncertain decisions. People also are biased by their perception of risk, as we will see. So all these things go into it. Now this slide is going to make your eyes crossed, but I want to show you all the modules we've built up before I get into some specifics. There are 7 different fundamental, actually 8, fundamental components to building up this capability. You've got to measure something. There's no such thing as monitoring without measuring. You got to put sensors in the field. 2, you have to have a fundamental model, hopefully physics-based, as much physics as possible, that can replicate your structure's performance in situ. You have to create, and this is critical, a fast-running emulator, because as I said earlier, you cannot run these complicated models all the time. That's usually a machine learning task. We create emulators for our slow models. We have to contextualize the system, all right? We take models of future load states, damage evolution, operational models, all stochastic, by the way, so we don't know the future, and we propagate that through to make a prediction of remaining useful life. RUL just means time to limit, time to limit. And a big part I'm going to focus on today, how do you make a decision then? And it's going to be based on risk, as you're going to see. All right, and then there's also a real-time decision-making component, because obviously if you're doing monitoring and, wow, the gate's about to fall off, you better do something now. No time to do a decision analysis, right, if it's obvious. Okay, you can imagine what people call this. It's such an overused term, I hate it, but it's a digital twin, just like Iron Man. It really is. We're trying to recreate the Iron Man movie. I love that film. That's Iron Man getting ready, you know. That's what we're trying to create for our digital underwater inland waterways navigation corridor. It has to do all these things. It is hard. We've been doing this for 7 years, and we've just made a dent in one of the corridors. It's really, really hard. So before I get into the details, what's risk? Make sure everybody's on the same page. I'll try to be a little bit unmathematical for the moment. It's just a measure of the probability of times the consequences of a decision. Usually an adverse decision, a bad decision. That's risk, okay? This actually is from North Carolina. I couldn't believe I found this. A prom couple was taking a picture in front of an F4 tornado. That's risk. That was several years ago, 10, 15, I can't remember when the site was taken. But, you know, everybody, and then once you assess the risk, you have to decide what level of safety you want. It's the measure of the risk that's acceptable, because there's no such thing as zero risk, all right? So you have to have an acceptable margin. We're engineers and we get it. Communicating this to the business world's hard. Everybody wants certainty, okay? There's a framework for doing that. Okay, now a little math. It's before lunch, so I can get away with it. The way we're fundamentally underpinning, pulling that concept of risk into decision-making is through starting off with something called Bayes' theorem. Statistics is a powerful thing. If any of the grad students in here haven't taken a probability and statistics class, do it. It's required in our curriculum, but if you haven't done it, it'll change your life. So what do we want if we're doing monitoring of a structure over its life cycle? We want the probability of observing all the structural states we care about, the damage state, given that, vertical line, we measured something new. Pretty simple. That's what we want. If we could have that, I'm going to the bar. I'm done. All right? But we don't have that. We need to somehow get that. And Bayes' theorem gives us a powerful, powerful way to do that. Okay, through the total probability theorem, you can derive this. Basically, what we want can be represented as what we can estimate or model, the probability of observing that data in a known state, conditioned on a known state, times any prior information about that state divided by the total evidence, which is just a number. It's a constant for any closed problem. So it actually doesn't enter into the problem. You can make that a proportional, and that's fine too. So that's how we start, okay? Because we can handle everything on the right-hand side, all right? Now is where we make the leap over to economics. Well, actually, one more step. Sorry about that. How do you discern between the differences in information? If you look here, what if you're in state 1 versus state 2 versus state 9? How do you decide, right? You might be in those states. Well, detection theory, another class you should take, they do it over in EE, but structural engineers should take it. Detection theory is a method to quantify the ability to discern between information-bearing patterns under inevitable uncertainty. And it's just a hypothesis test. Is it more this? Is it more this? And they've already solved this for us. We don't have to do any math. It turns out that the Bayes uncertainty detection solution is to just minimize the loss of decision errors. Ooh, we're starting to see now the connection. When you make a decision, you want to minimize the total impact of your bad decisions. And that's where you should draw your decision boundary in whatever feature space you're doing. So that's been proven and done, and it turns out picking between any two states is just a ratio of likelihoods. That's what the right-hand side of that last equation was. Just a ratio of two things. The probability I'm in one state versus divided by the probability I'm in another. All right? And if I can derive or estimate that transformation for a given decision state, just as math, I can convert data to the decision boundary. Now that I have that, I can go to economics. And it turns out, there's a formula, the total expected value of a loss for any decision you make, given the design of how you're making the decision. So inherently behind all this is that you've put a monitoring system of some kind out there. And that's what E represents. It's all the design variables, sensors, what you're measuring, how you're getting the features. And if you just integrate all the data, there's some function L. It's just called a loss function. This is where you talk to the customer. The customer knows what it costs them when they screw up. They should know. Okay? The engineer might have to model all the right-hand side because then we can use Bayes' theorem. This is all engineer. This is a combination of engineer talking to the customer. That's the financial side. So a large part of this talk is going to be talking about modeling that L function. And if we discretize it, because in SHM we often just make discrete decisions, I could turn an integral into a sum, and it's just a whole bunch of probabilities, weighed probabilities. So this is the probability of making a certain decision, right, times the consequence cost of making that decision. And isn't that what risk was defined as 5 slides ago? So here we are. Now we have the math behind an actual value of cost, assuming you use the right units, because probabilities have no units. We have a measure of cost. Okay? All right, so 4 objectives that I wanted to do. I'll show a little bit on each one. We're going to exploit that expected utility theory. How do we get the L function? Incorporate the effect of behavioral tendencies in the final decision, because we're all biased, whether we like it or not. Develop a framework to quantify the benefit of installing an SHM system. Should we even use it? Sometimes we found out it doesn't make sense. There's no business case. And then optimize the advantage by optimizing how the SHM should be designed. Because if you've got all this, if you can calculate total risk over a life cycle, you've just figured out a framework to optimize. You want to minimize that, right? That's what most customers want to do. They want to spend the least amount of money over the life cycle. So, again, we have these miter gates. We have our damage state, cracking. I'm mostly interested in the gap loss because that often causes a critical failure where the gate literally is sitting at the bottom of the river. And we have a design space, which I'll get to later. You could put sensors here, there, everywhere. You can measure this, measure that. That's a sensor space. So we have an asset. It has to be instrumented, okay? And then we compute, using Bayes' theorem, the posterior observation space of observing the state given that we've measured something, okay? And there's a whole lot of uncertainty in this problem. The water levels, sensor noise, environmental parameters. I'm not even going to talk about modeling errors, but that's huge. Yes, we fully acknowledge there's modeling error, could be modeling errors. There's a Kennedy O'Hagan framework for dealing with that, but I'm not going to worry about it today. Keep it simple. Most maintenance engineers will tell you, I just want a binary decision. Do I need to fix it or not? End of story. I don't want a complicated, multi-dimensional decision space. Okay, so we have 2 actions. Do nothing, keep operating. This is a simplification, obviously. Do sequential maintenance. So that's our space. So the whole point is you don't want to do nothing if you're within some tolerance of a limit. Similarly, you don't want to waste money doing maintenance when you don't have to. You have to shut it down, blah, blah, blah. There's costs. 2 wrong decisions. So you got 2 correct decisions and 2 wrong decisions in a binary space. So any given instant in time, we need the posterior distribution of the damage. I'm not going to get into the details. We have to use sequential Monte Carlo particle filtering to prognosticate. This is what I'm going to focus on. Base consequence cost and the risk perception of the decision-making engineer. What do I mean by base consequence cost? This is that L function. Basically, this is some idea, the way we're going to start a simple way of modeling it. It gives the net cost, or net consequence, of making a decision D when theta, the damage state, is true. So in our case, there's two possibilities. So if we're going to make decision to do nothing, given, and then the action of doing nothing, and the true damage state is okay, not limit state, there's some still minimum cost associated with that. Cost of operation, whatever the normal cost of operation is. So none of these are 0, but there's always a cost. If the true state is damaged, okay, and we say it's undamaged and we take action that's not consistent, there's some cost associated with that. That's a false decision. Similarly, this is another correct decision. It's the cost associated with having to take the asset out of service because your SHM told you to. That's going to have something. And then there's the other bad decision, saying it's damaged when it isn't, which is a false loss. You still got to take it out of service, perhaps, but you just lost economically. So this is completely assumed. As long as you have a monotonic function, think of the x-axis as damage intensity, progress toward limit state without any maintenance. Damage grows, it has to, otherwise you violate entropy. Damage can only grow. You can just linearly interpolate between those 2 costs. You could do something else. We can argue that all day, but just for the sake of right now, we're going to linearly interpolate. Human decision makers have to come in now, and they skew that. They skew that perception. Everybody in here has a different perception of risk, right? Should I drink 2 beers and drive? 1, right? We've all been there. Let's be honest, okay? So it's the same idea. Are you risk averse, risk neutral, or risk seeking? Okay? The risk profile of the final decision maker turns out can be mathematically modeled by their what's called utility versus wealth curve or loss curve. We borrow this from economics. It's called a utility function. So an individual's private utility gives him or her evaluation of the consequences of the action. And it may be different from the actual monetary cost. Some people don't want to do maintenance right away. They're going to take some risk. Or other people, anytime there's the slightest, chance that there's something wrong, I don't want the boss to get after me, I better do maintenance. And it's all going to come down to the various consequence costs, and they're skewing. So there turns out to be a 2-parameter function that can skew risk-neutral behavior. Okay, so your perception of risk can be simply characterized by 2 things. All right, and that's how we're going to get these utility functions. So by choosing these 2 parameters, as you see there, C and gamma, we can essentially parameterize risk profile, okay, and get really, really risk-averse behavior versus really, really risky behavior, okay? This is all from behavioral economics. But it's important for the decision maker to understand that. You can even do this by making those variables stochastic and averaging over an organization. You can actually generate an organization's risk profile. We did that for the U.S. Corps of Engineers based on their maintenance records. Anybody want to guess which side of concavity they operate on? Are they risk neutral, risk averse, or risk seeking? Anyone want to challenge that? Yeah, they're violently risk averse. If there's such a thing as violent risk aversion, the Army Corps is it, okay? Civil engineers, am I insulting civil engineers in the room if I say they tend to be that way? That's why we build bridges with a safety factor of 20, okay? They're just, risk averse because the consequences are high. The consequences are high. All right. So we can parameterize that, and then what ends up happening is where the critical loss occurs depends on one of those parameters. So for example, a risk-averse organizational profile might look like that, and a risk-seeking organizational profile would push that function to a lot higher loss level that they can tolerate, right? Think of it, you almost have to think of this like gambling. And in fact, they often use gambling words in this. So in this case, ORP1 is a more risk-averse organization than ORP2, okay? What we might mean by that is ORP1 organization tends to conclude that the gate is damaged at a much smaller damage level than the other one, and they're going to do something because they just don't want to tolerate that risk, okay? And so you can then take this function and weigh, right, that utility that we've already calculated. You can and add that into the utility function in Bayes' risk, all right? So, but we have most of the pieces now. How do we do decision making? There's a formal process of decision theory, all right? And prior decision analysis is, I have to differentiate among two different kinds of decisions. When you have no SHM, because you don't have information coming in yet, you just have the design and maybe you have past history. Okay, so you have to use your analysis only. That's called prior decision analysis over a life cycle. And then you have posterior, where you start collecting data. So prior is, just like we said 5, 6, 7 slides ago, you want to find the expected value of the utility function. Okay? You define the loss by the utility function, the mean value of the utility function, and the best decision for some risk profile characterized by those two things is given by D prior, the minimum decision boundary that minimizes the cost. Very simple. Let's minimize the cost. Remember, there's a lot of complicated things that go into that capital psi. That was, all that crazy math several slides ago. Now, let's say you did decide to invest in SHM. Posterior decision analysis. Now you make the same expected of the utility, but it's conditioned on data, plus the cost of getting that data. That costs you something to develop an SHM system and maintain it, keep it out there, right? So that's a trade-off. And then it becomes still a minimization. Minimize that over the decision space. So, decision-making framework has to include all the uncertainties. The world's highly uncertain. Importance of model updating. Getting data from out in the field is important if you can be done. And I'm going to conclude this in a bit by saying, how do we decide whether that data is worth it? And the other contribution here is the importance of behavioral biases. Okay, all of this is now into the global function. So when we get that expected value, how do I know? So what? The number, it's a number. We minimize the decision space. We have this series of sequential decisions we make over the life cycle. How do we evaluate all of the decision space? Well, it's just, did we save money or not? It really is that dumb of a question over the life cycle. When you look through all the sequential decisions, through all the propagation, through all the uncertainties of the asset model, the amount saved minus the total costs associated has to be positive, right? If E, value of information, is positive, we're in good shape. So this is the system design, cost of maintenance and operation, and this is the expected reward. How much risk have you bought or willing to buy down by making better decisions using that SHM, or if you didn't use it, not data? All right, so investment risk, and you can put it straight into economic terms. Investment risk, reward, okay? And you can create level sets as a function of initial SHM design cost, and then whatever your maintenance and operation costs are, tack on risk profile behavior and find out the regions where it makes sense to invest, because you have to make this positive. All right? Whoops. And if you're really risk averting, you're way down here. So essentially, okay, this is where it makes sense to invest. This doesn't. For all the curves, depending on where your risk profile sits in the procedure. So, again, I know there's two ways you could do it. We introduced a new metric sometimes you can actually make a great paper simply by taking what was a difference and turning it into a ratio. A whole paper out of just turning a difference into a ratio. Turns out that this ratio of reward to risk has better properties compounded over time. It's normalized, so it's a little bit more robust. So we want the cost saved over the life cycle. Here's now where I've put in all of the complicated statistical parts of Bayes' risk into those formulas with that fundamental utility function that I have. The goal is to save more than we spend, okay? And if that VOI is greater than 0 or our ratio is more than 1, we should invest in SHM, as I said, those level sets, okay? So here, for example, are a whole bunch of degradation curves of an unmaintained gate. That's the growth and damage over time. Not so much early in life. You tend to have a growth phase, and then you might tend to have a sort of annealing phase almost. But then near the end, it runs, near the end of life. So that's a family of uncertain curves, okay? If we have all of these things, plus that, we can look at a life cycle, not just a single decision, but life cycle. So there are those curves again, all right? Those are the cost classifiers that answer the question, what's the range of SHM system cost for it to be feasible? So again, this is the range of feasibility, have to be on this side of the curve, all right, to make it feasible, okay? So that's what I just said, all right? And you can imagine that as the amount of risk aversion increases, the flexibility to choose a system decreases. The more scared you are about taking risk, not surprisingly, you don't have a lot of ballpark to play in, to invest in a monitoring system. And so the final thing, okay, if we can make sequential decisions that minimize the total life cycle, now I can optimize. Okay, what can't I tune all the SHM parameters, where the sensors go, et cetera, to then minimize the cost further? We've decided to invest in a nominal SHM system. How do we optimize it? Well, we can run this whole process and minimize target Bayes risk as a function of design now. This is an awful problem. And you'll see why in a minute. It considers the varying risk of structural failure over different time periods, and it considers the whole cost of operating the SHM system. So again, there's our gate. Now, what we're going to do, once we get to here, this has to be run thousands and thousands of times, because we have to simulate all the possible life cycles this structure has to go through, all right? And, and including the maintenance strategy, whatever the organization tells us the maintenance limit state is in maintenance strategy. So, to do the optimization, we want to quantify the net savings as a result of deploying a certain design of SHM system, okay? There's two stages of this. There's the design stage. This is the prior stage. We don't have SHM yet, all right? So we have our physics-based pre-posterior analysis, all the uncertainty. You can choose to model sensor malfunction even if you want. That's important. Sensors aren't perfect. And then you have your prior damage degradation model, what you think the range of failure progression should be, and run it through the pre-posterior optimization over the life cycle, and that's where your sensors should go. That's that's the design. No data's been taken, nothing's been deployed, but it's a starting point. Now, if you're on the lower side of that SHM curve and you have this design, go. You put them in the field. This is what we told the Army Corps. Put it in the field, and let's start collecting data, all right? Once you start collecting data, you start to narrow down things like the degradation curve. You start to watch your uncertainty collapse. You can update the model from the data based on the newly acquired sensors, and then you can update the sensor design, assuming it's movable. Strain gauges are a pain in the ass, right? Taking them off, but in principle. If you're using a drone, you just change where it looks. That's easy. Change the path planning. That's the operational stage. So, you don't have to measure risk to reward ratio. Just as a side comment, you can also just maximize the amount of information by adding a sensor. You don't care about the cost. Cost be damned. We just want more information. Okay, that's a different objective. You can consider the possibility of a sensor malfunction. I won't explain the details of how we modeled that, but we did. We assumed that the sensor's response itself had a reliability. Or, what I just showed you, best use of budget over the life cycle. That's another objective. And then the operational stage, evolve the design with time. Again, you can use information, you can use budget, and you can choose to either do a fully new design in the future or just add another sensor. Either way, it's up to you and your customer what's allowed. We just make a comment here that it's better to normalize all these VOI, value of information metrics. You want them to be unitless so that numbers don't blow up or get too big or small. You know, like regularizing a matrix, that kind of thing. It has better behavior, so we want to normalize them in such a way that they're bounded between like -1 and 1 or 0 and 1 and this kind of thing. Okay, and then finally, here's why it's a hard problem. For our miter gate, the design space is 10 to the 78,170. You know how many atoms in the universe there are? Less than that. We can't compute that, right? We're done. We might as well go home. So we have to use approximate Bayesian computation, and we can't just let the whole design, we have to constrain the design space. And that makes sense. I mean, you can't put a sensor anywhere anyway on the structure. So you start to constrain it, and then you use Bayesian optimization, which is just basically an expected improvement. We decide to go with the add a sensor routine only when it adds value. Okay? And so at the design stage, we did a design. I showed you this before. We gave the core for different objective functions in case they didn't like our maximum cost, where they should be putting their initial allocation of sensors. And it's not a particularly surprising place. That's where the loads are. In this case, it's not so hard. It's where the main loads are. And that's the pre-posterior. And this, well, I don't know why thought I got rid of this animation, but here is the expected value of information, which maximizes after just adding 2 sensors. This is important. They're not gaining, they're only losing money by continuing to expand the SHM system after that under this framework. Okay? Now, it may be that at some point data come in where a reevaluation might change these a little bit, and that's okay, right? But that's what these kind of updates, and we assumed a moderate risk aversion profile here. I should have run this. It's so painful to run. I should have run for a risk averse and a risk seeking profile. Risk seeking profile probably would have stopped at 1 sensor. Risk averse would have probably, the VOI peak would have moved out to the right. So anyway, with that kind of information, then you can actually show when they're going to have the cost savings maximized in their life cycle, right? Helps people decide how they want to manage a future budget based on what the observed organizational risk is. And you can see some of the things that make sense. You see a shift in the peak towards smaller damage levels as your aversion increases, as you get more nervous about making decisions that are going to cost you something. These are just some results in the 3D space for different risk profiles, number of sensors, and the reward to risk ratio. You can see a random design of sensors produces random behavior. You can see that the expected value of budget optimization gives you the highest risk to reward. Okay, and we even included a uniform, which isn't really random, it's a uniform grid, and it's still lower. So it really is truly a framework that will give you, that will tie the engineering uncertainty to budget. And so basically we just did that. So those were our steps. And then we can update it in time as the variability decreases, right? The more certain you are about the future as data come in, the more you can make truly dynamic updated designs. So we do that by just monitoring variability, coefficient of variability in the updated RUL estimates, okay? And we can find the optimal time to add the next sensor by considering the coefficient of variation curve obtained by using the damage evolution model and the optimal variation curve by whatever risk function you're using. So that depends on the application, okay? And when those cross in time, that's when you add a sensor. Because you don't want to put SHM out in the field maybe on day one. The structure's new, unless you're retrofitting. Structure's new. So it may not make sense to invest until the future. In here, we told the Army Corps on this new gate they should invest at about 11 months. Those are months. They need to start monitoring, okay? And, well, that's a bad, sorry about that. I don't know what happened there. Okay, and then so we compared to what would happen if they did a fully new design versus a design by adding just a new sensor one at a time. And it's really up to them how they want to choose it. It turns out that by doing a fully new design, we actually get slightly better control over controlling the variability in the future. But it's slight. I wouldn't call it a massive improvement in this application. That may not be true for all applications. All right, so maybe that could be potentially too expensive or too painful to do or impossible just get on the application. But you can just keep updating the design, and you stop when that VOI goes negative. So, you know, these are some of the conclusions for that last bit. You know, if you can't be perfect, be reasonable. Right? This uncertain world. Well-designed sensor systems actually buy you big edge in investment than just throwing some random design out there. But reward always comes at a cost. No free lunch, right? No free lunch. You have to do, in my opinion, you have to do VOI. You cannot convince your customer to invest in SHM unless you do this kind of analysis. Okay? So, oops, that's just me. I said some of these things. Here's my final comments. We're creating a digital twin. From our definition, it has many functions. Basically, it's entire life cycle management. We're using risk-reward analysis and based on utility theory. I think that's really powerful. It's convinced me. It's all data-informed. Okay, model-initiated, data-informed. And it gives an actionable edge because it ties performance to measurable outcomes that the business people who give us money like, all right? So, I think we'll end there. Thanks for your time.
All right, there's some time for a few questions. Right,
yes, so very interesting talk. Will your design be sensitive to what kind of damage model you're feeding?
Absolutely. You're absolutely correct. So, This whole example was based on that single failure mode of loss of contact. If I were doing distributed cracking, completely different sensor design. You're absolutely right. We've done that. I didn't have the results to share today, but absolutely correct. Yep. The degradation, I'll make a more general preachy comment because you ask a good question. And this, you know, I'm the editor of the SHM Journal. So if any of you do SHM, you know, I get to see your paper. Professor Ewan's on our board. He's a colleague and does a lot of things. But, you know, if I were to define how most SHM papers 10 years ago were, it was collect data, take the square root of the sum of squares, call it a metric, future work. There was no decision. There was no uncertainty modeling. There was no understanding of tying why you're taking that data to the business case. And the way I relate that to your question is you've got to know what you're looking for. In the 1990s, when my field really started taking off, you could get money simply by going to NASA, if you're aerospace, or to the FHA, AWA if you're civil, and say, I'm going to put 1,000 sensors out there. That was a proposal 30 years ago. And you get $1 million to put 1,000,000 sensors on, 1,000 sensors on a bridge. The Hong Kongers did that. The Stonecutters Bridge. They have some of the best monitoring in the world on their bridge network in Hong Kong. That's because that's what they did in the 90s when it was good to get money. Can't do that anymore. There's no actionable edge. You have to define what you're looking for. If you don't define what you're looking for, SHM's dead. Yeah.
If I'm thinking about the state of health of a structure, and I can do things like I can predict crack growth and so on and so forth.
Yep.
But when I repair a structure, its health state changes.
Absolutely.
And where do you take the baseline? Because a repaired structure may not be as good as an original structure.
Correct.
So how do you define where the baseline goes after?
That's a great question. And again, I didn't include, if you guys had given me 2 hours, we have modeled that. It's a great question. So when they actually choose the D1 option, go do something, maintenance, they go repair it, they dewater the damn thing, and it takes days and months, and then they weld or whatever they're going to do to fix the problem. And then that repair, it's supposed to be highly tolerant to, or highly prescripted by maintenance procedures, but there's variability. So what we do is we recover the damage curve to a stochastic fraction of where it used to be. So we say it can't be better than it used to be. Maybe it can in some applications. In fact, one of those is, just as a side comment, is when they invented fiber-reinforced polymer seismic wraps to go on bridge columns in the 90s, this bridge was actually stronger than the original concrete. But, and then that becomes just yet another uncertain variable. And so those degradation curves that I showed, I guess they went this way. With maintenance, they go like this. Oh, repair.
Right.
But that where we drop it to is one of the random variables. We just add it in as a new stochastic variable. So it's a good question. Unless they, and the only way to verify what the statistics of that are is to have really good maintenance records, which the Army Corps doesn't have. So
I'll piggyback on that question. The damage occurs. How the damage occurs also plays a role.
How it occurs.
Like I say, a boat is coming.
Okay.
Hits the gate by mistake.
Absolutely.
Or a log that comes in a storm and comes and hits the gate.
That's right. There's actually a lot of that. There is a lot of that.
So
yeah.
Would the wage damage also matter in the model?
Absolutely. If you have an overload event, let's take your example. This happens all the time, surprisingly, but boats smack into the walls of the chamber. Yeah. I don't know if anybody on the Mississippi's full of logs. So is the Ohio. So if you have an overload event, what you have to include in those, and again, I didn't show them here. This is a great question, but we have a probability that the curve will have a very large state change instantly. There is a probability associated with that, so you're absolutely right. And if you include that in the degradation modeling, that there's a possibility for a rapid change in damage, you're correct.
And it could also be hidden in the sense that the log hit at the bottom of this and you can't see it, and you don't have a sensor there, then you can't see it.
Yeah, I mean, again, that's what you the best you can do is in your prior design account for it. But if you didn't, you can't. I mean, you can learn from it later when your gate's sitting at the bottom of the Ohio River, which they've done.
Thank you, Mike. My question is more about from most of the engineering research, we always put time on the verification. With this modeling, could you comment on how you can verify those models, the effectiveness of the model?
Yeah. So the original model can only be verified in the sense of predicting as-is condition, right? So in this case, once the gate was instrumented, a whole bunch of non-damaging event, just normal operational events were all measured and correlated with our model to ensure that the predictive strain coming from the gauges was what the model said. So it was validated in the nominal state. Until we get damage, I mean, that's the problem in SHM. You can't do supervised learning in civil structures. You can in bearings. I mean, if those of you might study a loop, you fail a bearing, who cares? And you might have data, acceleration data. You don't have too many failures here where we can actually see how did that actually relieve the strain. So it's not validated on failure. It's only validated on normal operation.
But also prior data, it's not sufficient.
It's not sufficient, no. Mostly because the Corps hasn't instrumented anything until the last 5 years. Very little. That's sad. But
Very similarly, the nuclear power station side
Yeah.
doing something similar.
Yep. Yeah, well, the nuclear world, you guys use really strict reliability-based design and standards. I mean, this is similar, reliability-based design, except this is more damage-tolerant design as opposed to safe life.
Since we're on the subject, I was curious as to whether or not the Navy has been looking into something like this for dry docks or for nuclear power plants.
The Navy actually uses this precisely not for dry docks or anything like that. They use it on the Littoral Combat Ship 2, the LCS-2, for hull monitoring.
Really?
So my previous job before San Diego, UC San Diego, was Navy. And so we designed a lot of some of the original ideas that are the company that took it forward was Metis Design Corp in Boston, Cambridge, whatever. And but they're using risk-based monitoring methods on LCS. To my knowledge, they haven't adapted it for dry dock. I think the next generation composite mast of submarine is going to be using it. So, but yeah, the civil applications you mentioned, I'm not aware of them being interested in this.
So if you have a very risk-averse organization...
Like the Navy.
Absolutely.
That's why you're saying this, I'm sure.
I worked
Yeah.
for NAVSEA for 3 years.
I was at NRL, so
Beautiful.
yeah, you get it. Okay.
So does the risk aversion, I mean, it makes it more flexible to install new systems, but does that also affect their willingness to have personnel install these sensors? Because clearly structures like dry docks, miner gates, they're dangerous structures, and you really don't want to put your personnel at risk unless you have to.
Yeah. So, well, I guess the one way I'd answer your question, which we have not done, but could do with this framework, is model. So right now we just have what we call the cost of of deploying an SHM. That's where you would have to include in that cost the risk. We might just put in a material cost or the time of an engineer to weld the strain gauge or a diver to go underwater to do whatever. There's a cost that they know, but we didn't necessarily model the risk to life or the risk to safety of those people. That could be done. That's another layer of complexity that could be added. But the framework would accommodate it, though. Yeah.
Mike, I was thinking that this framework can also apply to aerospace structure.
Absolutely.
It can be a little
Yeah.
bit easier because you have to look into section of the wing. All things are
Yep.
But they're more visible, right? I mean, in an aircraft situation, external visibility is fairly easy, whereas in this case, if it's under the water, it's a lot more challenging
Yeah.
to visualize that.
Yeah. Yeah, so in fact, if you're interested, I mean, we for the Navy, but for the aero side, we showed them an optimal sensor design based on risk. We compared it to just maximizing probability of detection, which is what most people like to do in your community. They're not as interested in risk. They're interested in, I just need 90-95 or whatever. I need POD. Max the POD. That's a different objective function. I didn't talk about that. I talked about it 10 years ago when I was here. But maximizing the POD does not necessarily give you the same sensor design as minimizing the risk. Those are different objectives. But the framework is the same. It's just what objective do you want to use in aerospace? Maybe Boeing would minimize risk. I don't know.
How can you tie in the risk into the CPM, the condition-based management?
Well, that's essentially what's being done here. It's essentially, right? I mean, there's an adaptive, we're always doing a value of information analysis every time data come in. You could apply this as to a simple rotating piece of machinery much simpler. It'd be a lot easier. Please, let me have some funding to do this on a spindle. That would be much better than a miter gate. And constantly update what data is needed to make a risk-informed decision about when failure is going to occur. You still need a degradation model. You need to know how the bearing is failing, or if it's rotorcraft, whatever. You have to know the failure modes. But this is pure SHM. I think of condition monitoring as SHM, just a different application domain.
Mike, what you're trying to do is look at progressive failures, not sudden failures, correct?
That's right. But to go back to his question, all you can do is you can model as part of your degradation curve the possibility that you'll have a massive change in your parameter, your data state, because like a boat hits the lock or something. But so anyway, just with that caveat, you're right.
So for the most part, if you're doing progressive failure and not sudden events,
Mm-hmm.
In your description of a digital twin,
Mm-hmm.
you talked about scales, doing something fast, and that's why you need a reduced order model, and a more expensive model that can give you a lot more detail. So for aerospace, that applies a lot, because if I want to do life cycle predictions, I will use detailed finite element models and CFD models and so on. And if I want to do decision making on the fly, that if I have an elevator failure, or if I have this, what do I do? So for that, I need my quick model. I'm not very sure that I see the logic of why do I need that quick model in your scheme of things.
You don't.
Because, okay, so...
You're right, you don't.
But you mentioned...
Yeah, I'm giving you, the reason I showed you a complete framework is we actually apply this to a hypersonics problem, which needs, as you well know, very, very fast decisions on hypersonic trajectory decisions. So you're right. We didn't need, you're absolutely right. Nothing fast needed here. That's right.
All right, let's thank Dr. Todd again.
Thank you. Oh, yeah. That's right. Just later on. 619. Just text me real quick and I'll know it's you. 619-980-01. Okay.
I reserved the hello. Already.
Still not ringing. That's it.
Sorry, I have one precious.
I may not have good signal.
Yeah, you can use David Throckmorton was the ARWA fellow.
Hi. Thanks for your question.
We used to meet in a smart truck SPIE conference.
Yeah, now I haven't been to SPIE in the last 5 years.
Yeah, that time, this time, did you meet Jeremy?
Oh, yeah.
Yeah. He used to go there too.
I'm going this year, though.
This year I'm not going.
You're not coming.
I was there last year.
Very, very nice. No, thanks for coming. I'll see you later today.
Yeah. That sounds great. So you take your time because the next meeting slot is mine. So
Perfect. Okay.
Want to run, get some coffee if you need.
Probably water. Oh,
Water.
it finally rang. So.
Okay. All right.
So he's next on your
We'll walk in.
lunch.
Yeah, lunch we'll get
Ryu.
Joyce.
Yeah.
I think somebody has a schedule.
So Srinath, Fleming asked me a question whether he can bring when he was a young.
No, I already talked to him. I said if it's
Perfect. Yes, I remember you're on my
after
agenda.
4:30, then bring him the.
Great.
I think you were here years ago.
10 years ago. In fact, to the day, I was here February 9th, 2014.
That's
Please, yeah.
we gotta have a special celebration.
Yeah, I don't know how it worked out that Srinath invited
Yeah.
me. It was the last time I came. It was Fuguo who invited me,
Yeah.
and it was exactly 10 years ago. I thought that was amazing.
That's why you
Yeah.
need. We'll have more
Hi.
risk management in the afternoons.
Well, I told him, yeah, let's. Hey,
Chip. I'm
Hi,
one
Chip.
of Lori Virgin's.
Oh,
students.
fantastic.
Thought he was going to be here.
I
today.
thought he told me he was, but he wasn't 100% certain. See, everything's uncertain.
He's
He's
DGS now. So.
Yeah, he told me. I just saw him last week at IMAC anyway.
Okay,
so
so you didn't miss him too much.
He told me he might come. He would try. Plus, I know parking's a bear here, so.
Yeah, it's a little bit better than Duke. Duke parking
Duke is
can get a little rough.
So, what are you working on with Laurie?
We do mostly buckling of thin structures right now. So we've been at AFRL for a little bit for like circular panels.
Okay.
Just did some cylinder work, and now we're going back to do thermal loading on buckled panels in the natural frequency change.
Oh.
So can be interesting.
Yeah.
But you were at NRL, so I take it you know John
Nichols. He was. Even though officially, don't tell Laurie this, but I think Laurie would agree. Even though John was Laurie's student, he was really my first student because I did all the funding and he worked with me. He didn't stay at Duke. I took him to the NRL and he worked right next to me. So essentially, I was his PhD mentor.
Cool. I talked to him briefly. I was reading your CV and I was like, I bet he knows this.
Yeah,
guy.
John and I published many papers back in like 1999, 2000, 2001.
Cool. Yeah, he's a nice guy.
Well, he's big shot now. He's division head at NRL.
I had a call with him a couple of months ago. I was talking about Smart Fellowship. So
Fantastic.
just post-grad stuff. So cool. Well, nice to meet you.
Chip's nice to meet you as well. Please give Laurie my best and punch him in the nose for not coming.
I think he's a little tired of DGS, so I gotta give him some slack
He
on
was
that.
complaining about Bajan, so I get it.
Have a good one.
Thanks.
Hi,
Hi.
thank you for your presentation.
Oh, yeah, thank you.
I am Jasmine from Chile.
Oh, okay.
I am very interested in taking a PhD in San Diego.
Oh, okay.
I don't know if there is a possibility that I can apply before December.
Yeah, they will open up the cycle. The next cycle of admission starts in August,
August. Yeah.
all the way until January 2025.
Yeah.
Because it's already closed for this next fall.
Yeah, I know.
Yeah, yeah.
It's very difficult.
Yeah, it's the timing. It's unfortunately too late for this coming fall, but you should. We have a lot. Chile. We have so many Chileans students.
Really?
Yeah, because of earthquake engineering. A big part of our group, not my interest, but my department has lots of earthquake engineering. Lots of Chileans have earthquake problems. So
I love that.
yeah.
Yeah, but is there a possibility that they have a PhD position, or I must wait till December?
If you can find a professor, a faculty member who has funding, we've already given out all the first year fellowships, but if there's somebody that has funding and they're ready to hire a student and they can open up the application process for next fall.
That is on the page.
Yeah, you have to decide who you want to work for and talk to them and find out and meet with them about their interests and your interests.
Okay.
Yeah. But it's possible. It's not common, but it's possible. I've recruited students very late because I meet them late, and I just so happen to have funding. I need somebody. Perfect. So it can happen, but we have to go through paperwork, and you have to have a commitment from the professor to give you funding.
That's critical.
That's critical. Otherwise, we can't admit you.
Yeah, I have a offer now here, but
Right.
I am not interested in mechanical engineering.
I see.
Not me, right? Who offered?
No, you know.
It's like,
Well, I mean, structural engineering, yeah, so I don't know what your interest is, but look at our website, just redesign the whole thing, so I think it's really,
your program is unique.
It's unique.
Structural engineering, I guess.
it's the only one in the United States, which makes us both interesting and also a target for ABET. They hate it.
Oh, really? No,
They give us a lot of problems.
Yeah.
But yeah, it is an interesting program. We have, the world's largest outdoor shake table for civil. We just destroyed a 12-story building.
Oh.
For
I want that.
See, there you go. That's what you want to do. You need to talk to the earthquake and structural, civil engineering guys.
Okay.
Yeah, probably not me. I don't have any funding. Everything's funding in my group is already committed. But the earthquake and civil people, maybe they have some.
Okay. Thank you very much.
Yeah, well, sure.
Thank you. Bye.
Yeah, thanks. Yeah. I think I have everything. Yeah. Okay.
Important.